Hello everyone, welcome to this video. In this video, we are going to solve this question which states that we are given a group as the general linear group consisting of all 2 cross 2 matrices such that whose entries are taken from the set of real numbers. So that means we have all the matrices whose determinant is 0. This is what we have for this particular group, correct? The condition is that the determinant of the matrix should be non-zero. Correct. So for this group, we need to find what is C of this matrix. Now this matrix is obviously present in the general linear group. Why? Because when you calculate the determinant, it is equal to -1, which is not 0. Correct. Now we have to calculate the centralizer of this matrix. Now what do you mean by centralizer of any element? Centralizer of any element is a collection of that set which commutes with this particular element. So we have to calculate or find out the form of the matrices which commute with this particular matrix, because you know this group in general is not abelian. Here all the elements do not commute. So we will calculate or find out some particular elements which commute with each other. Correct? So for that we start with this set. The centralize by calculating this centralizer of this element. It would consist of all the matrices taken from our group G, correct, such that it commutes with this element 1 0 0 1 matrix, correct. So now we assume what is our X. X is consisting of 4 elements A, B, C and D, where A, B, C and D all are real numbers and such that this determinant is non-zero, correct. Now we put X in our this equation and then find out what is the value of A, B, C and D. And then once we know the values of A, B, C and D, we are able to calculate our X, correct. And this is what is required here for this particular part. So we consider this equation. We on the left hand side and on the right hand side multiply using matrix multiplication, and then we are equating the corresponding coefficient. So A plus B is equal to A plus C, then A is equal to B plus D, C plus D is equal to A, and this C is equal to this B, correct. So we have these 4 equations. You can further simplify to obtain that your C is equal to B and your D is equal to A minus B. So what we have done, we have put A is equal to A, B is equal to B. Instead of C, we obtain B. So instead of D, we obtain B minus A. So you see, we all obtain all of them in terms of A and B. So your matrix X, which was earlier A, B, C, D, could now be written in this form A, B, B, A minus B, where you had this condition previously that AD minus BC should be non-zero. Now you have the condition, instead of writing D, you are now writing A minus B. Instead of writing C, you are now writing B, correct. So you can simplify this to obtain A square minus AB minus B square. This should be non-zero. So this is what is the centralizer of the given matrix 1 1 1 0, right, where the entries are being taken from the set of real numbers, and we have this condition holding for this particular matrix, correct. Now let's move on to our second part, where we need to calculate the centralizer of this particular matrix 0 1 1 and 0. The procedure here in this case is also the similar one. Here we have to calculate the matrix X, which we have initially assumed as A, B, C, D, such that AD minus BC is non-zero, correct. The determinant is non-zero, such that this X commutes with the given matrix 0 1 1 0. So we consider this equation, solve the left hand side and right hand side, obtain these matrices and commute the and equate the corresponding elements from the matrices. Right, the elements having which are placed at the same position are equate. They are put equal, correct. So you obtain B is equal to C and A is equal to D. So from here you can replace D with A and C with B. So now you have, instead of C the value B, instead of D the value A. Here also you can replace C and D with A and B, so that you obtain this condition that A square minus B square is non-zero, or you can write that A square should not be equal to B square. Hence what is your X? Your X is a matrix of this kind, where the entries along the diagonals they are the same, correct. So this is the centralizer of the element 0, 1, 1, 0 present in the general linear group of order 2 having entries from the set of real numbers. Now let's move on to the third part, where we have to calculate the center of our element G, our group G, correct? Center of group. What is the center of some group? It is the set of all those elements from G such that this commutes with all the other elements of the group, correct? So we are collecting all those elements within G such that they commute with all the other members. So here I say the center is clearly this matrix, where what is this matrix? Here on the diagonal we have A, and off diagonal entries are 0, right? This is the form we would obtain. Now let me prove it. You would say how you reach to this particular answer and specify that A should not be 0 and it could be any other real number. I said if it is 0, it would be a 0 matrix, and when you multiply anything by a 0 matrix you get 0, so it cannot be 0, correct? This condition is obtained from this reason. Now let me prove that this matrix is in fact a center. How it is a center? If it commutes with all the other members of our group GL2, correct? Now what is A? A is some scalar, and what let us consider now two elements A and B. A and B are any two matrices, so that means if we specify A and B to be present in GL2, that would also be okay. Why? Because in that case only we have condition on the determinant, which would be the determinant of A and the determinant of B should be non-zero, correct? However, in general, if you have A as any scalar and if you take any two matrices, you have this condition that A into capital A times B. So this A could be shifted, right? It could be you multiply both the matrices first and then multiply A to it, or you multiply A firstly to the matrix B and then multiply the result with the matrix A, right? This is all the same. So let's mark this as equation 1. These kind of results we have, these are the basic results which we have studied in our previous classes, correct? Now if I is the identity matrix, then for all matrix it would commute with all the other matrices, correct? This is the property of identity matrix. So let's mark this as equation 2. Now clearly this matrix A0 0 A could be written as, you can take out A outside, so it would be A into I, correct? It would be of order 2. So clearly combining these two results, the result of identity and AAB is equal to AAB is equal to AAB, correct? So combining these two results together, now we wanted to prove that this matrix, which is nothing but A into I, so this A into I commutes with all the other members of GL2, so this AI here commutes with all the other matrices. So let's see how this is there. If you take small a into I into the matrix A, now because this is a scalar, using this property, this A could be shifted, this is capital A could be taken outside, correct? This is the property that this could be taken outside. So we have done the same, this I has been taken outside. So this is the result. Now because I is the identity matrix, so it commutes with all the other matrices using our property 2. So it would commute with AA as well. So it would be written as AA into I, correct? Now again using the first property, this A could be taken outside, so it would be this. And we wanted to prove just this thing. Hence this matrix A0 0 A would commute with all the matrices A taken from the general linear group having order 2, whose entries have been taken from the set of real numbers. Hence the center of this general linear group is AI, where what is AI? It is A0 0 A, where A is a real number which is non-zero. So I hope you understood this question well. Well, that is it for this video. Thank you for watching.